All right. Good morning, everyone. This is Mr. Turek for Physics CP doing another PowerPoint presentation on the subject of astronomy. In our last episode, I had tried to explain how the ancient Greeks figured out the size of the Earth. They figured out the size of the moon. They even figured out the size of the sun and the distance from the Earth to the moon and the distance from the Earth to the sun, all by using math and geometry, and physics. So amazing and true. Uh, first, the first step is noticing the sun and the moon are the same size in the sky, half a degree. Then pondering, well, if the moon orbits the Earth and it shines by reflected sunlight, then and if it's in a perfect circle going at a constant speed, then from first quarter to third quarter moon, compared to third quarter to first quarter moon, tells us an estimate of how far away the sun is. They established that the sun is very far away, taking advantage of lunar eclipses, estimating that the size of the Earth's shadow at the distance of the moon from the Earth is 7/3 the size of the moon. They were able to place the moon, sun, and Earth to relative scale. And then, based on research at the Library of Alexandria in Egypt and two measurements, they were able to establish the size of the Earth. And so that made everything else fit. That knowledge was just about wiped out for over 1,000 years and was the Dark Ages. So now I'm going to pick up the story with Copernicus in the 1500s. Of course, it's always great to talk about astronomy with pretty pictures along the way. So this is one my wife wants to do, and I've never done this picture properly, but I should. So I did a 10-minute test run last few nights ago. If you take your cell phone and download an app so that you can keep your cell phone camera shutter open for a long time and mount your cell phone on a sturdy, rigid object, a tripod or something, so it can't move, at night, when it's clear, you can take an exposure of the stars and you get these star trails. It shows that everything in the sky appears to be rotating around the north celestial pole. And there's a white dot not in the center. So, first of all, the white dot is the North Star. It's Polaris. That's right. It is not the brightest star in the sky. It is not dead center in the middle of all these arcs. It is about half a degree off from the center. And during your lifetime, Polaris will drift a little bit closer and closer to the north celestial pole. And then it'll drift away, and that'll be it for the next 20 some odd thousand years. The Earth is wobbling around in space. Each star, you can kind of start to tell, has its own color and brightness, but the camera was exposed for about 2 hours, I estimated yesterday, based on the arc length being about 30 degrees out of 360. And in this picture, the foreground is a highway lit up by starlight, some low-lying clouds, some house lights showing up on the hillside, and the beautiful northern hemisphere sky exposed above it. You can do this. It's fun. You should try it. Everything appears to rise in the east and set in the west. From our point of view here in the northern hemisphere, southern as well. Rise in the east, set in the west. Now, swimming against that daily motion is the sun, which appears to move east by about 4 minutes of time or 1 degree of motion each day. After the course of a year, that means the sun will have gone around the sky once relative to the distant stars. The moon also goes eastward each day by about 12 degrees. So in 1 month, the moon will have gone around the sky once. Okay, so if you want to see Orion the Hunter here in the month of March in the northern hemisphere, shortly after sunset, you can see it in the western sky. A month from now, each day the stars rise 4 minutes earlier and they set 4 minutes earlier. So a month from now, Orion will be closer to being in the sunset at sunset. And after a couple of months, you won't be able to see Orion in the evening sky anymore. You'll have to wait till early or mid August when you can start to see Orion rising just before sunrise. Okay, so the stars change with the seasons because really it's the sun going around the sky. Here's something that the ancients noticed. If you were to track the position of the planets over time, for the outer planets like Mars, Jupiter, and Saturn, they don't just go east across the sky the way the sun and the moon do. No, no, no. They go east, they stop sometimes, go backwards, which is called retrograde, stop, and then go forward again, which is called prograde. So, in this time lapse sequence of photographs spanning maybe several months, in the middle of, well, the brightest dot is Jupiter. The fainter moving dot is Saturn. As far as the stars go, in the center, a little bit up from center of the photograph, is a small, tight grouping of kind of bluish white stars. Those are called the Pleiades, commonly known as the Seven Sisters. Well, if you count the stars, you're going to count more than seven. But the myth is there are six sisters and they're looking for their lost seventh sister somewhere in the sky. Also, the name Pleiades is translated into a different language as Subaru. And yes, that is the little logo used by the car manufacturer. Subaru is that little pattern of stars that you see in the middle of the photograph. On the bottom left area is the brightest star, sort of orangey, is the star Aldebaran. And you might remember from a previous astronomy lecture that Aldebaran is part of the Hyades star cluster, and that V or parabola shaped grouping of stars there is the head of Taurus the bull. So, it's all real stuff. You can go outside and admire these things. The Pleiades are about to set in the evening sky, and Mars right now happens to be passing through the region of space where the Pleiades are in our sky. But why do the planets appear to go forward, which is called prograde, and then go retrograde, and then go prograde again? So here's a desktop planetarium animation showing the motion of Mars as we see it from Earth. So there it is, it's going backwards, and now it's going forwards. If you were to monitor the dates going by on the bottom left corner of this animation, you see it goes backwards for a few months. And just to tell you that, yes, these are the stars. The stick figures are showing the constellation outlines. So the backwards question mark in the upper right corner is the head of Leo the lion. The triangle connected to it is the back end of him. He's lying on the ground. And then Mars is just touching the constellation Virgo. So, stuff to learn, but the question is, why does a planet seem to stop and go backwards? So, here's the explanation that Ptolemy worked out thousands of years ago. He said Earth is the center of the universe, the green center. Mars is on a yellow orbit going around the Earth in this diagram. The distant stars are part of the fixed and unchanging celestial sphere. Mars is on an epicycle. That's the little red circle that's going around some invisible point on the bigger yellow circle. And as you can see, by sighting along the white line, that makes it appear that Mars is going backwards for a while and then going forward again. This model worked extremely well for predicting the dates of astronomical events like this. For thousands of years, it worked pretty well. But after the Dark Ages ended and the Renaissance began in Europe with a reemergence or an emergence, maybe, of critical thinking skills, people noticed that the model had drifted a little bit off over the centuries. And it was off by a day and a half now. Terrible. Well, some people wanted to tweak up the model a bit so that it would be as accurate as it had been thousands of years ago. Along comes some terminology. I'm not going to quiz you on this, but there are actually three vocabulary words from today's lecture. None of them are on this slide right now. But here is the terminology used by the ancients and modern astronomers when we talk about what we see when we look up in the sky with respect to the different planets. So there's two categories of planets. The ones that are closer to the sun than us, which is Mercury and Venus, those are called the inferior planets. The ones that are farther from the sun than the Earth, being Mars, Jupiter, and Saturn, those are called the superior planets, or superior planets, however you want to put the accent. The diagram on the left is for the outer planets, the superior planets. There's the sun in the center of the circles. The Earth is on the center circle, and Mars, Jupiter, or Saturn are on the outer circle. When they line up with the sun in our sky, that's called a conjunction. And really, that means they're on the opposite side of the sun from the Earth. The angle between the planet and the sun that we see in our sky is called the planet's elongation. As the planet, and by the way, the direction of planets in all these diagrams is taken to be looking down from above the north celestial pole of our solar system. And so therefore, everything is going counterclockwise. There's a little arrow saying east is to the right. And that means that's the direction everything seems to be moving. They seem to be heading to the east across our sky from day to day, month to month. The Earth is also spinning counterclockwise in these diagrams too. Okay, so when the elongation of a superior planet makes it 90 degrees away from the sun, that's called quadrature. And that means the planet is directly overhead at sunset or at sunrise. An outer planet can go and be on the same side of the sun as the Earth. And so that means it can be opposite the sun in the sky. Well, that's called opposition. Ta-da! Very logical. Now take a look at the diagram on the right for the inferior planets. These are just Mercury and Venus. They can never be opposite from us in the sky. So if it's midnight and you go outside and you see a planet directly overhead, you can be absolutely certain that it cannot be Mercury or Venus. It has to be one of the superior planets. For the inferior planets, yes, it can have a conjunction with the sun, but now there's two possibilities. It could be between us and the sun, that's an inferior conjunction, or it can be on the opposite side of the sun, which is a superior conjunction. And like all the other planets, it goes eastward, counterclockwise in these diagrams around the sun. There's the elongation, the angle between it and the sun as we look up in the sky. And there's a maximum angle that it can ever reach. That's called the greatest elongation. So the greatest eastern elongation is the farthest in the sky that you would see the planet after sunset. And the greatest western elongation is the farthest in the sky that you would see the planet from the sun before sunrise. And last week or so, Venus was west of the sun, and that means you would have to see it early in the morning just before sunrise. I suspect it's heading towards superior conjunction right now, but I didn't look it up. So those are the terms for different moments or angles for the planets as we see them from Earth. But wait, there's more. I said there's three terms I want you to learn today. Here's two of them: sidereal and synodic. The animations go really fast. Once you understand it, maybe you can keep up with the animations and understand what they're showing. Sidereal means one period of motion measured with respect to the distant stars. So write that down. Sidereal. You see it spelled in the title, Sidereal, or side real, as I humorously pronounced it sometimes to myself. Sidereal. One period of motion, that means 360 degrees of motion, one period of motion measured with respect to the distant stars. Synodic, Synodic, synodic is one period of time measured with respect to the direction to the sun. They're different. They're different because the sun moves against the stars. Synodic, again, one period of time measured with respect to the direction to the sun. And so in English words, that means from a full moon to a full moon. Okay, so that would be a synodic period for the moon, from full moon to full moon, as an example. From first quarter to the next first quarter, that's a synodic period. Okay, so now I'm going to talk you through the diagram on the left, which explains this with my excellent teaching skills. In this diagram, we're assuming that the sun, not the Earth, is the center of the universe. S for sun. The Earth can be on either one of those two planets. I'll put it on planet A at first here. So we're going to put ourselves as planet A, and therefore planet B is some sort of superior planet. We're going to line up along what you would call the negative x-axis if we were to put a Cartesian coordinate system centered on the sun here. Line them up where it says number 1. And we're going to have a race around the sun. All right, get ready, on your marks, go. You know from Newton's version of Kepler's third law that the period squared is proportional to the orbit radius cubed. And so that means every single time the object that is closer to the sun, the one that has a smaller radius orbit, is the one that's going to be moving both faster and in much less time to go around the sun once. So in every situation, planet A is going to go around the sun faster in less time than planet B. So in this diagram, the Earth on planet A goes all the way around the sun and gets back to the starting line labeled A2 for the Earth. So A1 and A2, A1 is at the starting line, A2 is at the finish line. And where is old slow pokey planet B 1 Earth year later? Why, it only made it over to B2. That is scarcely more than 1/4 of the distance around the sun. Now, yesterday I started measuring things with protractors, but I'm just going to approximate it and say if it only went about 1/4 of the way around the sun in one Earth year, then that means it would take it almost 4 years to go around the sun once. And by years, we mean Earth years. So, in the time that the Earth goes around the sun once, one Earth year, planet B has barely gone more than 1/4 of its orbit around the sun. Therefore, its sidereal period, measured with respect to the distant stars, is almost 4 years. Now, let's continue the race beyond one Earth year. So now the Earth at A2 goes racing around the sun a second time and catches up to planet B for the first time at position 3 on the diagram. So at A3 and B3, that's the Earth finally lined up with planet B. That is when the planet is finally at opposition for the second time, because the race began with planet B at opposition, opposite to the sun in the Earth sky. At position 3, we're finally back to being opposite, where planet B is opposite the Earth, opposite the sun in the Earth sky. That is the synodic period for planet B. And in this case, that was one full Earth year plus, let's round it and call it approximately 1/3 of an additional Earth year. The angle from A1 to A3, that's like 1/3 of an Earth year. So 4/3 of an Earth year would be the synodic period for planet B. While almost, so that's like 1.3, maybe 1.4 Earth years would be its synodic period, while its sidereal period was something like 3 point, maybe 8 years. Okay, so quite different. Now, oh gosh, so this matches the bottom right GIF that's running so fast. And it's trying to show that a sidereal period is what it is, and the synodic period is what it is. Okay, great. Now, let's switch the position of the Earth in the diagram. So we're going to be like the upper right animation. And I'm going to talk you through the left drawing. So now let's put planet B to be the Earth. And planet A is one of the inferior planets, either Mercury or Venus. Once again, we line up. The planet is at inferior conjunction. That means we look towards the sun and the planet might be directly in front of the sun. That happened in June several years ago. And so our physics students actually went over to Cerritos Public Library and used specialized telescopes, and we watched the transit of Venus going across the face of the sun. It's a rare event. Okay, so at inferior conjunction, Earth is at B1, Mercury or Venus is at A1, and again the race starts. Poop! And off we go. Well, Mercury or Venus go completely around the sun once, while the Earth is only lumbered along to position B2. It takes until B3 for Mercury or Venus to catch up to the Earth for the first time since the race began. From the point of view of the Earth, that means the synodic period would be about 1/3 of an Earth year, maybe 4.5 months, maybe on this diagram. while the sidereal period, the time it took Mercury or Venus to go from A1 and return to A2, that was much less than an Earth year. That might have been, like 3 months and maybe a week or so. So again, they're different. But that's the meaning of the two words. Sidereal is measuring the orbital period with respect to the distant stars. In other words, the time it takes to go through 360 degrees of orbit. And synodic is measuring with respect to the direction to the sun. Okay, so what are we going to do with this knowledge? So along comes Nikolai Copernicus in the mid 1500s, and he believed that the sun, not the earth, was the center of the universe. Now that's heresy, because somewhere in the Bible is a passage that says God stops the sun from moving across the sky for a few hours so that the good guys could gain the upper hand in some battle that was taking place. And so, if you take the Bible literally for everything, then that means the earth is indeed the center of the universe because it was the sun that was stopped. Okay, so if you disagreed with the church in the Middle Ages or earlier, you ran the risk of being stoned to death or burned at the stake or dumped in boiling oil, for all I know. Different punishments. None of them really desirable. But Nikolai Copernicus worked out this formula. And no, I'm not going to test you on the formula. But the point is, he worked out the formula that gives us the relationship between the synodic period and the sidereal period for the planets. So we can take our observations of the planets and then turn that into the orbital periods for the planets. Nice. But wait, there's more. So let's talk about physics, math, geometry, astronomy. Here's the third vocabulary word for you to learn: astronomical unit, abbreviated AU. As this diagram is showing, and I'm not putting it on the reference sheets, one astronomical unit is the average distance from the center of the sun to the center of Earth's orbit. So, as I was explaining to you, the third vocabulary word for you is one astronomical unit, shown on this diagram as 1 AU, the average distance from the center of the sun to the center of Earth's orbit around the sun. That is the distance scale that we've been using since ancient times. And in modern terms, it's about 93 million miles, or about 150 million kilometers from the sun to the earth. For those inferior planets, remember, elongation is the angle between the sun and the planet in our sky. Well, those inferior planets can never be 90 degrees away from the sun. They are always some acute angle. And if you bother with the geometry, what's shown here is when it's at greatest elongation. So when the angle between the planet and the sun is at its maximum value as it orbits around the sun, that must be the moment when it forms a 90-degree right triangle. And you love trig, you know trig. You know that if you have a right triangle where you know one of the sides, in this case the hypotenuse is 1 AU, and you know the angle, in this case the greatest elongation angle, you can solve for the other angle, you can solve for the other sides. And that means you can solve for the orbital radius of the inferior planet. So for Mercury and Venus, it's possible to just measure the angle in the sky between the sun and Mercury or Venus, and from that, determine the orbital radius of those planets. What about the superior planets, you ask? Well, so there's a technique for that as well. And knowing the sidereal period is very useful in this case. So that whole business about figuring out a formula that relates sidereal period to synodic period. Here's a diagram showing how it works. The sun is at the center of the universe. The earth is the inner circle going around the sun. One of the superior planets is at P, let's say Mars or Jupiter or Saturn. And at that moment, the planet is at opposition. It's in a point in space opposite from the sun in our sky. All right, so now count the days until the planet goes from being at opposition to when the planet is at quadrature. Because when the planet is at quadrature, that means it's at a 90-degree angle from the sun to the planet in Earth's sky. So once again, we have ourselves a right triangle where the distance from the sun to the earth is 1 AU. Now, to figure out what the angle is, we presume that that all the planets are in perfectly circular orbits going at a constant speed. So by counting the days from opposition to quadrature and knowing the speed at which the planets move in their orbits, for the Earth, it's a degree per day. So if it's 100 days, that's an angle of 100 degrees for angle ESE prime. For the superior planet, you have to say, okay, that's 100 days out of its sidereal period. Let's say its sidereal period is 4 years. Well, then that would be 25 degrees in 100 days. So that would give you angle PSP prime. And by geometry, by math, by physics, by subtraction, you can work out what is the angle of that right triangle, the one that's not the 90-degree angle. And once you have that angle, you can calculate the orbital radius of the superior planets. Again, just by looking up in the sky, using a calendar, some math, some physics, some geometry, some reasoning. So here's the result that Nikolai Copernicus got in the mid 1500s. The column on the right is our modern accepted value, taking into account that the planets are on a little bit elliptical orbits, not perfectly circular orbits. And of course, by definition, the Earth is 1 AU from the sun. So in units of astronomical units, you can see his results were pretty darn good. The problem is that it's heresy to say that the sun is, all right, Tennessee, it's heresy to say that the sun is the middle of the universe. So Nikolai Copernicus waited till he was just about dead. He was on his deathbed when he finally gave his publisher permission to publish this book. And Nikolai knew it was going to be a very controversial book, so he titled it The Revolution. And then he died, I guess. So his publisher didn't want to get burned at the stake either, so he slightly changed the title of the book to On the Revolution of the Planets, implying that they're talking about orbits of the planets. And that, of course, this is just a mathematical model for calculating distances and periods, I guess. So, anyways, mid 1500s, this got published. Okay, so Nikolai Copernicus, the hero of the day for that. Now, religious beliefs prevalent in Europe in those days was that the Earth is the center of the universe, that the stars are fixed and unmoving, some sort of celestial sphere, that the planets, that the moon, for example, is in heaven, and therefore it's a perfect surface, that the sun is in heaven, so it's perfect. But What happened in the late 1500s is that there was a guest star that appeared. A supernova explosion took place somewhere in our galaxy, and a couple of people saw it, and that caused them to challenge their religious beliefs and to pursue a career in astronomy, basically, or astrology, as it might have been known back then. So I think this is not even a actual photograph. This might be a photoshopped thing. But on average, about once every 100 years or so, somewhere in our galaxy, there's a supernova explosion. And when it goes off, it's possible to show up in our sky as a bright star that suddenly appears and then fades away over days or weeks or months. In 1987, there was a supernova in the nearby Small Magellanic Cloud galaxy, and that showed up as a sudden new star in the southern hemisphere. So I went down to the southern hemisphere a few months after it appeared and could still see it and take pictures of it and such. It was named Supernova 1987A, if you want to look it up. But this particular supernova in the late 1500s went on and inspired one particular character that we care about, and his name is Tycho Brahe. On the right is a modern photograph of the supernova that he saw when he was young. And today, it's expanded by millions and millions and millions of kilometers, and it's just spreading out into space. And that's the debris of a star that you see there. The drawing on the left has a little subtle mm, uh, piece to it that I am going to explain to you. So Tycho Brahe loved astronomy and studied math, went to college, and he got into a dispute with, I don't know, maybe it was his roommate in his dorm or someone, but he got into a dispute with someone about the correct answer to a math problem. Well, when you're in college, you tend to do stupid things on occasion. And he decided to resolve the question of who had the right answer. The proper thing to do would be to have a duel, a sword fight. So, in the course of the sword fight, Tycho Brahe ended up with his nose being cut off. For the rest of his life, he did not have a nose. And he felt rather embarrassed about that. So he would have fake noses built, sometimes out of wood. For special occasions, he had a silver nose and would stick it on his face, maybe with hot wax or something. So, ouch, that's how he got his nickname, Silver Nose. Notice that the fact that he lost the sword fight implies that he was not correct with his math answer either, right? I mean, he lost. But what he was very good at is persuading the king of some small European country to fund the construction and operation of the Uraniborg Observatory. If you Google it today, there's nothing but a little mound of one wall left of the grounds. But this was the ancestral equivalent of our modern jet propulsion laboratory. So today's JPL in Pasadena is the command center that designed, built, tested, operated, launched, and landed on Mars the Perseverance rover, the nuclear powered Martian rover that got there just earlier this month, I think, or in February. Well, Uraniborg Observatory was the place for researchers and scholars to congregate and share ideas and investigate the heavens. Now, this is before the invention of the telescope, and yet it is crucial to our understanding of the solar system and the universe in general. So examine the diagram, the wood cutting, whatever it was, on the right that showed the key part of what made this such a treasure. In this image on the right, there's a wall on the left side, and way up on the wall is a small window. That's a transit window. So it was aligned to point exactly south. When you sighted along the sextant curve, whatever that's called, the huge arc of a circle measured off with degrees on the foreground of the image. Presumably, the well dressed person in the background, pointing towards the window, is Tycho Brahe himself. And yes, he was very meticulous about making sure that every night the operations were carried out as precisely as possible. So it wasn't like he just got funding for it and then uh, partied, you know, night after night. He went to his observatory night after night. Probably partied as well, but I don't know. The point is, note the work of the three assistants in the foreground. So, sighting along that arc is some guy who's looking through the window, and what he's doing is he's observing a star or a planet. And he's doing it right at the moment that it's crossing the meridian, we call it, the highest point in the sky for the day, for your location on Earth. So let's say it's Mars. And on this day, at this time, Mars appears to be 48 degrees above the horizon. I don't know. I'm making this up. And so he's had to move his eye until it's at the same angle on the little indicator there. And you can see this indicator is precise to better than a degree. Now there's a second assistant in the bottom right holding up a candle looking at some sort of timekeeping device, some kind of clock. And the assistant in the bottom left is writing all this information down into a notebook. The name of the object, whether it's Betelgeuse or Mars or Aries, what star or what planet it is, the date, the time, and the angle at which it was crossing the meridian. For 20 years, this data was collected for as many objects as they could see through that window on as many clear nights as nature provided. Tycho Brahe wanted to update Ptolemy's models that were off by a day and a half here in the late 1500s. And he thought this data would be key to helping him do it. But as you've seen by the result of his sword fight, he was not a master mathematician. The proof being that he had his nose cut off, right? So, although he struggled with it for quite a while, he couldn't do it himself. And Tycho Brahe was sort of a hybrid thinker that said, well, the Earth is still the center of the universe, but all the other planets go around the sun, and the sun goes around the Earth. So that was his thinking. Eventually, he hired a sickly mathematician to assist him in figuring out the corrections to Ptolemy's model, to update the model using all this data. And the guy he hired was Johannes Kepler. So around the year 1600 or 1601 maybe, Kepler was hired. And Kepler also, big into astrology / astronomy and mathematics, was eager to get his hand on those 20 years of notebook data from Tycho Brahe. But Tycho Brahe didn't really want Kepler to steal credit for it. So Brahe would have Kepler work on it under his supervision or so. And Kepler bragged and said, okay, in 2 weeks, I'm going to update Ptolemy's model and make it more precise. He did. In just 2 weeks, he worked out a better tweak to the mathematics of epicycles and orbits and all that stuff. And he got Ptolemy's model way better than being off by a day and a half. In fact, I would say if we do the math, his model was off by a quarter of a degree. Now, it takes 4 minutes to go through 1 degree. So that would be 1 minute of time. So Kepler updated the model and it was off by 1 minute of time, if I've done this correctly in my head. I guess that's right, right? 15 degrees in 1 hour is 1 degree in 4 minutes. So a quarter of a degree would be 1 minute. Interesting. Okay, and by the way, the sun and the moon are both half a degree in diameter when you look up in the sky. So if you were to look at the moon and measure the distance from the center of the moon to the edge of the moon, the radius of the moon, that would be the size of the error in Kepler's model after 2 weeks of work. But Kepler knew about how careful the measurements had been collected at Uraniborg Observatory. And Kepler couldn't believe that the data could be off by 1 minute of time or by 1/4 of a degree. He just no. He said that can't be right. Well, Tycho Brahe eventually died, and Kepler was able to get complete control over the notebooks. I don't know with the help of his widow or without the help of his widow, but somehow Kepler got a hold of the 20 years of data and went to work on it and said, okay, I'm going to figure this stuff out. It took him 10 years and over 500 sheets of calculations. But eventually, he did work it out. And here's the clever way he went about doing it. He believed, like Copernicus, that the sun, not the earth, was the center of the universe. And so he put the sun in the middle, and then he drew a circle around it, and he labeled that the earth. And out of all the planets and stars that he could have picked from, he chose to analyze the orbit of planet Mars. If he had picked any other object, he would not have had the revelation that he got by working with the planet Mars. So we are very fortunate in modern times that Mars has the characteristics that it has, and that Kepler had the perseverance that he had. So Kepler picked a date where Mars was at some arbitrary point in its orbit around the sun. But thanks to Copernicus, he knew what the sidereal period was of Mars. And so he could go through the 20 years of data and find a different Earth year in which Mars was back at the same point in its own Martian orbit around the sun. And on those two different dates, the Earth would be at different points in the Earth's orbit around the sun. Maybe on the first date, Earth was at E1, and years later or earlier, when Mars was again at point M, Earth was this time at point E2. Well, knowing the angles from the sun to Mars as viewed in our sky from Tycho Brahe's data, knowing the sidereal period from Copernicus, Kepler was able to triangulate and draw the two lines that intersect, showing this is exactly where Mars is when Mars is at that point in its orbit around the sun. And Kepler did that for about 9 points spread around Mars's orbit around the sun. So very painstaking, right? You have to work out how many days, what date of the year it is, and on and on and on. And then finally solve for the exact distance from the sun to Mars for each of those 9 different data points. Well, if there had been epicycles, it should have shown up. What Kepler discovered is in this diagram. And so if you pay a little more attention to the orbit of Mars, you'll see it is not a circle, not centered on the sun. It's actually slightly elliptical. In this diagram, Mars is closest to the orbit of Earth. And on the opposite side of the sun, the orbit of Mars is farthest from the orbit of the Earth. And so this is pretty much to scale the elliptical orbit of the Earth and Mars the way they really are. And so from this, from those 9 data points, Kepler worked out that elliptical orbit of Mars and his 3 laws of motion. So around 1609, Kepler was able to say the planets orbit the sun in elliptical orbits with the sun at one focal point. Second law, a line from the sun to the planet will sweep out an equal area in an equal amount of time. That's really from calculus, and no, you're not responsible for it today. Modern times, you and I don't need to worry about that. True, interesting fact. And his third law, the sidereal period squared is proportional to the orbital radius cubed. Okay, that's his third law. Now, I've been teaching it to you as Newton's version of Kepler's third law, which says t squared equals 4 pi squared r cubed over gm. Kepler didn't have m, he didn't have r in meters. Meters hadn't been invented yet. What he had were astronomical units and Earth years. So if you want to do Kepler's law in his units, you would do it in units of astronomical units and Earth years, and then it's just t squared equals r cubed in those units. Okay, so here's the explanation for why it looks like Mars goes backwards in retrograde motion. The answer is we go zooming past Mars. When we're both on the same side of the sun, we're on the Earth, we're on the inner orbit closer to the sun, so we're going faster than Mars. So the white line shows, oh, we go zooming past Mars, and that makes it appear as if Mars is going backwards or retrograde, when in reality, it's always been heading east the whole time. It's just been going slower than us. Ta-da! And here's the results of Kepler's calculations compared to, I guess modern values. The point is, to within about 4 significant digits, it works out very well. Yay! So thanks to Kepler 1609, we have the divorce of astrology and astronomy from each other. We could say that Kepler was maybe the first astronomer, meaning astrologers aren't really using mathematics to predict the motions of the planets. They're using other techniques, I'll say. And whereas astronomers are now just embracing mathematics and physics and geometry and saying, okay, this is the path we're going to go down as we understand how the universe works. And finally, here's a picture of the Crab Nebula, a supernova explosion from, I think, the year 1024 AD. And so now this one has exploded and expanded this much. In your lifetime, you will be able to see some of the expansion. Uh, you'll be able to notice the expansion. So if you compare a picture from when you're first born to just after you die, yeah, okay. So just before you die, you should be able to see uh, some actual expansion of this thing. All right. Well, there's another PowerPoint, and I need to get to it because the period ends in 3 minutes. Well, I'm going to do this PowerPoint in 3 minutes. So let's go. Boom. Bright star. Galileo. I've already explained how in 1609, late 1609, 1610, winter 1609, 1610, he pointed the telescope at the sky and was amazed with what he saw. He discovered craters on the moon. Remember, that's heresy because the moon is supposed to be perfect. He discovered the moons of Jupiter. And now you can understand, okay, they go whizzing around Jupiter, obeying Kepler's laws. Kepler desperately tried to have Galileo confirm Kepler's formulas, but Galileo didn't want to get burned at the stake for being a heretic. So Galileo never responded to any of Kepler's letters. Galileo observed that Venus goes around the sun based on its phases. Galileo discovered sunspots, the first European to report them. Chinese had been watching sunspots for thousands of years. And again, that's heresy because religiously the sun is supposed to be perfect without blemish. Countless stars, more countless stars. That is the Big Dipper. It's not actually a constellation, it's an asterism. The North American Indians used to use one of the stars as a vision test because it's actually a double star. It's the middle star of the handle of the Big Dipper. Those are the stars Mizar and Alcor. Thanks to Newton, we don't have to worry about the combined effect of planetary mass. We can treat it as just a point mass. We have weighed the Earth, and it's very hard to do. This is a very, very difficult measurement. And Newton published his work in the 1700s, and it's his understanding that if you travel 5 miles per second parallel to the Earth, you will actually orbit the Earth. You will fall towards the Earth, and the Earth will fall away underneath you. The surface will curve away underneath you, and you'll be in orbit. So when rockets are launched, they don't go straight up. They bend over and they speed up to go parallel to the Earth faster and faster.